Of your 5 senses, 4 are liars. Not malicious liars, but meticulous editors. Every sight, sound, and touch you perceive is first sent to a central sorting office deep in your brain called the thalamus. The thalamus is the great gatekeeper, a neural relay station that processes, filters, and then forwards sensory data to the cortex for conscious thought. It decides what you need to know. But one sense, the most ancient and primal, was granted a secret key. Smell cheats. The olfactory nerves, the only neurons in your central nervous system directly exposed to the open air, bypass the thalamus entirely. They don't ask for permission. Instead, they forge a direct, unfiltered superhighway into the most primitive and powerful parts of your brain. The amygdala, your seat of emotion, and the hippocampus, your architect of memory. Evolution, in its relentless optimization, created a radical architectural anomaly for this one sense. Why grant olfaction this privileged, direct access pass to the neural vaults of emotion and memory? This anatomical peculiarity isn't just a curious footnote in a biology textbook. It is the fundamental clue that smell operates on a completely different and far more profound set of principles than any other sense. For decades, the explanation seemed simple, elegant, and wrong. We were taught the lock and key, or shape, theory of olfaction. The idea was that each odor molecule has a specific shape, and it fits into a corresponding shape-matched receptor in the nose, like a key into a lock. This unlocks a signal to the brain, which we perceive as a smell. This model's intuitive appeal made it a staple in textbooks. But its predictive power quickly crumbled under scrutiny. It failed to explain glaring paradoxes. For example, molecules with vastly different shapes can smell identical. The sprawling, complex structure of a sandalwood molecule smells uncannily similar to simple borane compounds, a chemical that looks nothing like it. Even more damning, molecules with virtually identical shapes can smell entirely different. Take ferrocene and nicolecene. They are structurally identical twins, yet one smells like camphor and the other has a metallic chemical odor. The shape theory has no answer for this. It cannot explain why you can distinguish a heavy water ice cube from a regular one by smell alone, despite their identical chemistry and shape. The lock and key model is a scientific ghost, a zombie theory that still walks the halls of academia but has been evidentially dead for years. The key doesn't fit the lock. In fact, there might not be a key at all. The answer came not from biology, but from the strange world of quantum mechanics. In 1996, biophysicist Luca Turin proposed a radical new theory, initially met with ridicule. We don't smell a molecule's shape, we smell its vibrations. His theory suggests our olfactory receptors act as nanoscale quantum tunneling devices. Here is the mechanism. Inside the receptor, an electron is ready to travel from a donor to an acceptor site. The odor molecule sits in the middle, creating an energy barrier. In classical physics, the electron shouldn't have enough energy to cross. But in the quantum world, it can tunnel through. Crucially, this tunneling is not free. The electron can only complete its journey if it can transfer its energy to the odor molecule. And it can only do that if the molecule is vibrating at the exact right frequency to accept that energy. Each type of molecular bond, a carbon-hydrogen bond, an oxygen-hydrogen bond, vibrates at a characteristic frequency, like a tiny tuning fork. Your nose, according to Turin, is a biological spectrometer. It's not looking at the molecule, it's listening to its chord. A molecule that smells of almonds vibrates at one frequency. A molecule that smells of roses vibrates at another. It's a mechanism known as inelastic electron tunneling, a process well established in solid-state physics but thought impossible in the warm, wet, chaotic environment of biology. A revolutionary theory requires extraordinary proof, and for years, Turin's vibrational theory struggled to find it. The smoking gun evidence arrived in 2011 from a study by Franco et al. On fruit flies. They presented flies with 2 versions of the same molecule, acetophenone. The 2 versions were chemically identical and had the exact same shape. The only difference was that in one, the hydrogen atoms were replaced by deuterium, a heavier isotope of hydrogen. A heavier atom means a slower vibration, like a heavier string on a guitar producing a lower note. If the shape theory were correct, the flies should not have been able to tell the difference. But they could. The flies overwhelmingly avoided the heavier deuterated molecule. They were smelling the difference in atomic mass, a difference only detectable as a change in molecular vibration. This was a direct contradiction of the shape theory. Later, in 2013, a human study by Gain et al. Confirmed the finding. Humans could easily distinguish between regular musk and its deuterated, heavier twin. The deuterated musk was described as smelling burnt or toasted, a clear perceptual difference. This isotope evidence is the cornerstone of the vibrational theory. It proves that our noses are sensitive to the quantum-level property of nuclear mass, not the classical property of molecular shape. It's the biological equivalent of hearing the difference between a violin and a viola playing the same note. This brings us back to that strange anatomy and the Proustian phenomenon, the uncanny ability of a scent to trigger a vivid, involuntary autobiographical memory. Why does the smell of rain on hot pavement not just remind you of summer, but transport you there, complete with the emotional texture of a specific moment? The quantum theory provides an answer. Because smell bypasses the thalamus, the scent memory isn't filtered, edited, or contextualized by your conscious mind. It's a raw data feed. Furthermore, the vibrational signature of a scent is informationally dense and unique. It's not just smells like a cookie. It's a specific chord of dozens of molecular vibrations from flour, butter, sugar, vanilla, and the Maillard reaction. This high-fidelity quantum signal creates a neural signature of unparalleled specificity. Research by Hertz and Schooler confirmed that odor-evoked memories are consistently more emotional, more detailed, and feel more real than memories triggered by any other sense. This is because the quantum information of the scent is being directly written into the hippocampus alongside the raw emotional data from the amygdala. It's not a memory of a memory. It's a quantum resuscitation of the original encoded experience. Your other senses tell you a story about the past. Smell lets you relive a single vibrant page. If you find quantum detection in humans hard to believe, look to nature, where this technology was perfected hundreds of millions of years ago. Consider the male emperor moth. It can detect a single molecule of a female's pheromone from up to 7 miles away. Let's be clear, not a cloud of pheromones. A single molecule. Experiments by Dietrich Schneider in the 1950s measured the electrical impulses from a moth's antenna and confirmed they were responding to individual molecular impacts. A classical lock-and-key system cannot account for this level of sensitivity and specificity. The probability of a single key finding a single lock over miles of turbulent air is practically zero. However, a vibrational model works. The moth isn't searching for a shape. Its antennae are tuned to resonate with a specific frequency, allowing it to pick up the pheromone's broadcast with unbelievable efficiency. This quantum advantage also solves a major data problem. Humans can distinguish over 1 trillion different odors, yet we only have around 400 types of olfactory receptors. A shape-based system would require millions of receptor types. But with the vibrational theory, the brain uses combinatorial coding. It's not one receptor for one smell. It's the pattern of activation across multiple frequency-sensitive receptors that defines a scent. A few hundred types of vibrational detectors can combine to create a virtually infinite palette of smells. Nature didn't build a massive library of locks. It built a highly efficient quantum synthesizer. The world's most expensive and secretive chemical industry has been unwittingly practicing quantum chemistry for centuries. Perfumers, with their talk of notes, chords, and compositions, are using the language of frequency and vibration, not shape. When they create a fragrance, they are balancing the vibrational spectrum of molecules to create a pleasing sensory experience. The synthetic molecule Iso-E Super is a perfect example. It's famous in the industry for smelling woody and amber-like to some people, and faintly floral or completely odorless to others. This isn't just subjective opinion. It's likely a reflection of genetic variations in our quantum detectors. Different people's olfactory receptors may have slightly different electron donor acceptor energy gaps, making them sensitive to different parts of the molecule's vibrational spectrum. When the original nitro musks, prized for their rich scent, were banned for toxicity, chemists struggled to replicate them. They could synthesize molecules with the exact same shape, but they didn't smell right. It was only when they created molecules that mimicked the vibrational signature of the originals that they succeeded. Major fragrance corporations like Givaudan and Firmenich now invest heavily in computer models that predict a molecule's scent. These models are only successful when they abandon shape and incorporate vibrational data, essentially reverse engineering the quantum principles Luca Turin proposed. If the sense of smell is a finely tuned quantum system, it stands to reason that it would be one of the first things to break down when the brain's delicate machinery begins to fail. This is precisely what we see in neurodegenerative diseases. One of the earliest and most reliable predictors for the onset of Alzheimer's and Parkinson's disease is anosmia, the loss of smell. This can occur 5 to 10 years before the more familiar cognitive or motor symptoms appear. Why? The quantum hypothesis offers a chillingly logical explanation. These diseases are associated with systemic failures in a cell's ability to manage energy and maintain coherence, through mechanisms like mitochondrial dysfunction and protein misfolding. This could disrupt the precise energy gradients required for inelastic electron tunneling in the olfactory receptors. The quantum signal becomes noisy, weak, and eventually silent. The sense of smell, therefore, is the canary in the coal mine. Its failure is a direct, measurable indicator of a breakdown in the fundamental quantum biology of the nervous system. This is paving the way for revolutionary diagnostics. Researchers are developing quantum noses arrays of nanoscale sensors tuned to detect the specific vibrational signatures of disease biomarkers in a person's breath. Dogs, who can already detect cancers, Parkinson's, and even COVID-19 by scent, are likely honing in on these same quantum signals of metabolic decay. So, your nose is not a simple chemical detector. It is a quantum device, a biological spectrometer built by 400 million years of evolution to decode the vibrational universe. Every breath you take is an act of subatomic physics, as electrons tunnel through molecular fields to create neural patterns that bypass your conscious mind and write directly to the hard drive of your memory. This is why smell is the only sense that truly feels like time travel. It isn't a metaphor. The scent of your childhood home doesn't just remind you of the past. Its preserved quantum signature allows your brain to momentarily re-inhabit that past's unique emotional and neurological state. You are quantum tunneling to a memory. This science is now leaving the realm of theory and entering our technology. From NASA's eNose monitoring the air on the space station to the promise of smelling virtual worlds in a way that triggers genuine nostalgia, we are finally beginning to reverse engineer the quantum computer we all carry in the middle of our faces. The next time someone claims quantum mechanics has no place in the warm, wet world of biology, ask them to smell a rose and then explain the feeling that follows.